Okay, so now we're looking at Archimedes principle, and we had a bunch of notes we took during class, and we determined how we could see that the wood floated because its density was less than that of water. Uh, so we had these steps. I don't have those notes in front of me. I wonder if I even took a picture. We'll see. Propagation of uncertainties, right? So we've done this before. Well, let's see. Verification of the measures are said to agree if x minus y squared is I see. That's another way of doing it. We do something very similar. So what it's saying is that the difference between them squared is less than or equal to the adding together the plus minuses of two numbers. Nice. From dimensions, from using Archimedes principle, and this is very similar to what we do. So this is the difference between them squared less than the square of the plus minus on each of them. So what we do is that we take the delta V from, and we'll use the same nomenclature. I just don't want to write there. Okay. Well, I got an idea, maybe because I unplugged and replugged this thing. Mapping. Yeah, it's mapping everybody. I don't want that. I just want the one screen. Okay. So what we do is we take the well. Okay. The plus minus of the V from measuring it divided by that with the measurement and times 100. And we do the same thing with the plus minus of V from Archimedes over the volume from Archimedes times 100. And we get the percent difference between the two. Excuse me, the percent error on each one. The percent difference is, and this is a standard way of doing it, is we take the absolute value of the two, of the difference between them, and then we divide by the average of them. And multiply by 100. And what we want to know is that this percent difference is smaller than the other two, because the other two basically represents an error bar. So if the percent difference is bigger than those two error bars, then that means that there's something wrong. And in this case, let's see what they're doing. If they're adding together the error on both of them, which is basically a hypotenuse of a triangle, the delta x squared plus delta y squared. And if the difference is less than that, then that's interesting. I remember this sort of. But if you want to do it that way, but it's not a way we've been using. Okay, yeah, and there's some other notes. This is nice. Somebody was nice enough to write those things out for you. Right, so you get a plus minus on the volume, just like we've done in the past. And the plus minus here, now how does one assign a plus minus onto this one? That's a good one. Measure the volume. So for us, Oh yeah, it's about the plus minus on the masses we weigh, and I suppose one could add some for what? This is a toughie. I forget how this one. No errors. Error analysis is requested for this part. So I don't get it. We're supposed to compare them. Okay. The kind of mass uncertainty. Okay, so we can see it. So what it looks like is what we do is we see how good we are. So we're testing Archimedes' principle by seeing how well. So we can determine that. Now I'm getting myself back up to speed. This is what happens when you wait too long. So what we want to do now is we want to say, okay, we have we can do a percent difference here. And then how can we assign, measure the apparent mass with the, use these, verify as, does the dimensional volume of the brass agree with Archimedes' volume? And I seem to remember, yeah, I don't have it right in front of me. Okay. All right. So we went over that during class period. And then, let's see, hang the bug. And then we went over having to force the wood underwater, and we figured out how to get the actual buoyant force on the wood. And so that would be number one here. And so what did we have going on here? We had the buoyant force of the wood and going up. Then we have the weight of the wood, and we had the brass, the weight of the brass minus the buoyant weight of the brass. And that's already in our notes. Determining the density of the buoyant force was found by subtracting the apparent weight combination in 2C. So that must be when the brass is submerged. So then we know now the buoyant force on the brass. And then from the apparent weight combination of part 2D. So meaning when we immerse both of them, then then we know how much is just like before. We get a buoyant force of the wood. And okay, so an object floats in a liquid. Use equations 1 and 2 to prove that the fraction is equal to the density ratio. Okay, 1 and 2. And let's pause this for a moment. Alright, I got objects 1 and 2, and we want to create something that looks like, scroll this down a little bit, row object, oops, so it's going to be, what's going on here? Okay, row object divided by row of the fluid. So something floats when its weight and the force of buoyancy are equal, basically. So I mean, that's actually whatchamacallit, the condition of neutral buoyancy, but it should work. So we can set the two of these equal to each other. And so if we set the two equal to each other, then the acceleration of gravity goes away. So then we have rho of fluid times volume displaced, that's how much is underwater, equals rho of object and the volume of the object. So this is a classic cross product looking thing, right? So if we can divide by rho of the fluid, so then we get rho of the object times volume displaced divided by rho of the fluid equals, oops, what did I do wrong? Volume of the object equals the volume displaced. And now I divide both sides by V of the object, so I get rho of the object divided by rho of the fluid equals V, the amount that's submerged, what displaced, divided by the volume of the object. And that is what we would expect, because we did something like that. Rho of the object over the classic expression, the weight of the object. So if the rho of the object is less than water, then the force of buoyancy holds it up. If it's greater than water or whatever fluid, then there's not enough force of buoyancy to keep it above the water. We went over that in class. So I expect to see that kind of thing and your discussion of how you got there. And then now we answered question 1 in class. I kind of went over it a little bit. You have to have some, the error propagation I'm having an issue with. We can do, in the case here, we can do error propagation on the volume, and then we don't have an error on the accepted value, but we just do the, in that case, what we want is the percent difference between Archimedes and, so you would be comparing either one of these two, and you need to use the volume. You need to calculate rho, right? So you can calculate rho from Archimedes, and you can calculate rho from simply measuring it, and then you can get, and you can compare either one of these to the accepted value. And then you're also, and qualitatively, in a way, you're demonstrating the conditions that something has to float. And we went over that in class. Okay, so another one down. I'll get this one uploaded. Maybe. I thought I hit the stop button. Let's try again.